Hi, my name's Alan. I'm going to present work titled Refining Process Descriptions from Execution Data in Hybrid Planning Domain Models. And this is work done with Santi, Franco, Rubiya, Reba, and McCluskey. And we all started at University of Huddersfield. Santi's now at Royal Holloway, and I'm at Heriot-Watt. The problem of traffic management has been set as a PDDL plus problem, and in that model the transfer of vehicles through junctions is modelled as continuous processes. So effectively the green light comes on, you turn a tap and vehicles flow at a constant rate. Whereas in observations of vehicles flowing through a junction, that's not always the case. So certain things can impact on it. So at the very beginning of when the green light just turns on, you usually have a warm-up period. If there's congestion, then it might change the speed that cars are travelling at. Okay. So the idea in this work is to start with a domain model, a PDDL plus domain model, and some observations from an environment, and then learn a model that explains the difference, and then use that model to refine your original model. And the target for this is to take our original process and then create a set of refinement processes. So there's going to be conditions that kind of partition the original kind of space that the process acted in, and then there's a refinement factor associated with each set of conditions, and that's going to be in a more appropriate effect for that more specific situation. So our approach starts by choosing some features. So we've defined a simple grammar which allows you basic operations over the propositions and functions in the domain model, and then we allow either expert selected, hand selected, or a kind of typical feature selection approach. We test both. And then we set the problem as a machine learning problem, and in this case it's multi-targeted, so for each of the effects of your process we learn a different refinement factor. We're going to use tree learning, and then we're going to try and compile that model back into PDDL+. So to get our machine learning problem, at some given time during a process, we observe the state, and we then, so that's then used as an example that we then kind of extract information for the specific process, and in this case we just use the parameters in the process header. So this is kind of focusing and allowing us to treat each of the examples in a consistent way. And the targets are then the observed divided by the modified, so modelled, so we're learning a factor. So in terms of feature generation selection, when we're going from our frame to the data point, the machine learning problem data point, so we use the functions and propositions of the domain model, and we use the kind of common operations to combine them up to some depth. So this is the functions, obviously. So for example here we can get terms like occupancy divided by capacity, which is kind of helpful in traffic. And then our two feature selection approaches, either expert assisted where the expert selects some appropriate features, or auto, where we use a filter-based approach based on correlation. So once we have our tree, in this case each path through the tree from the root to the leaf is going to be turned into a new process. So you can read the conditions down as you descend the tree, and the refinement factor is at the leaf. So in this case, if there's high density or congestion on the inlink, and the process has just begun, then we have this factor of 0.4. Okay. So at the bottom we have the actual process, and you can see that the condition is just added to the precondition, and the kind of factor is just used to modify the effect. So in terms of efficiency, we created different models using trees with different number of nodes, and then we simulate the same plan using each of the models, and this is just simulation time, which kind of increases as the model becomes more complex, but it seems to be in a linear fashion. In terms of simulation error, in this case we simulated plans using a traffic simulator, and then we simulated the same plans in each of the models, and in the kind of original model we get higher error, and the expert assisted gets the best, performs best, the least error, and that's the same in the second network we tested. With the blue's the original model, and green's the expert assisted. We then tested it in terms of planning. So in this case we have the same goal in each case, and we use the new model to actually plan with, and in the original, and then we actually test it in a traffic simulator, and this is kind of trying to gauge how close it got to the actual goal. So in original, which is the right one, overestimated flow, the middle is expert assisted, and the left is auto, and the two learned models, two refined models had better accuracy, and in the other network, again the original model overestimated flow, it's still on the right, and the expert assisted was performed well again. The auto, so it seemed to overfit to the plans in the training set, and its plans that it was generating were quite different. So in conclusion, we presented an approach for refining hybrid planning models, which exploits observation data, which can hopefully reduce the knowledge engineering effort in creating PDDL plus models. We've used the kind of traffic management scenario as a case study, and we've observed kind of improved performance. In this work, we were using a fairly limited feature space, so that's certainly one of the things in future work, is to consider other feature spaces, and also kind of how to balance, how to make the balance between model accuracy, planning time, and kind of cost of accessing real-time information. Cool. Okay, thanks.